Good afternoon, everyone. My name is Swati Singh. I'm a PhD second year student and working under the supervision of Dr. Lana Narayan at Auburn University. She is also here today. I'm going to present on visualizing UAV based detection and severity assessment of brown spot needle blight disease in loblolly pine forest. Let's start with the problem statement. Pine forests in the southeastern United States are under serious threat. And the reason of that threat is brown spot needle blight disease. This is a fungal disease caused by L. acigola fungus. This disease has been documented in 36 out of 67 counties in Alabama. Here is a very short video recorded from Mavic 3M multispectral video. It is showing the loblolly pine wealth in the study area. Here you can also observe some brown stands in the study area. So I'm going to share the multispectral UAV framework, how to detect these brown stands in the study area. So this disease results in substantial needle defoliation that are seriously impacting the tree health, quality, and the density. So let's take a closer look and try to understand how these symptoms appear on the small needles. So here is a very irregular round shape, red color spots, brown spots, followed by red and yellow bands on the pine needle. And these symptoms basically starts from the base of the crown. The reason of this disease is starting from the crown is that this fungus is moisture lover and highly influenced by the soil moisture. All of you might be thinking, how can these small symptoms can be detected by UAV remote sensing? The answer to this question is that UAV captures a very high resolution imagery in different spectral span, and by using these imagery, we can classify the disease or non-disease tree. So in our case, we have used DJI Mavic 3M multispectral drone. There is another small video. This is how multispectral see the forest area. So we have classified the healthy tree when there was no visible sign available on the stand, and then early disease when one third part of the canopy was infected, and then moderate tree when more than one third and less than two-third part of the canopy was infected, and then the severe when more than two-third part of the canopy was infected, and then crown dieback when the top of the crown was empty. That means there was no foliage available, and the dead when there was no foliage available at any cost. So the overall goal of this study was to develop a framework using multispectral UAV remote sensing to detect brown spot needle blight disease in loblolly pine forest. And the specific objectives are: first, to utilize UAV multispectral imagery, integrate with the machine learning algorithms such as support vector machine and artificial neural network to detect and map the distribution of healthy and disease tree in the study area. Second was to evaluate the performance of point cloud derived metrics from UAV multispectral imagery for individual tree detection in quantifying the diseased and healthy trees in the study area. The figure 2 is showing the study area, which was Washington County in USA. We covered total 9 plots, and we collected ground data as well as the multispectral UAV data in the study area. This slide is showing the methods. Let's start and let's have a look how we extracted the information from these multispectral imagery. First, we collected data in the from the multispectral drone, and then we performed structure from motion technique, from where we converted the 2D data into 3D data. After that, we align or stitch all the images and generated the dense point clouds. And then we optimize these dense point cloud to generate the very high quality digital elevation model and digital surface model, and which was useful for extracting the tree locations and the points. This was the result of the objective 2, individual tree detection. And for the objective 1, we have utilized the image aligned images and created a very high quality orthomosaic map for the study area. After that, we remove the unnecessary noisy part from the orthomosaic map and subset the study area. After subsetting the study area, we generated 5 vegetation indices. These vegetation indices are NDVI, NDRE, GNDVI, GDVI, and SAVI. By using one of these vegetation indices, we perform the soil masking to remove the soil from the study area and give the total focus on the trees. After that, we performed spectral susceptibility to analyze how effectively we can distinguish between healthy and infected trees. After that, we overlaid the ground data and generated ROI, performed classification and accuracy assessment, and finally, we generated our brown spot needle blight disease distribution map for the study area. So data processing and analysis was begin with the removal of the soil background. We have utilized NDVI threshold value of 0.25 to remove the soil background from the study area. Here in figure 3, you can see before and after the study area site of the soil removal effect. And here this figure 4 is showing the spectral profile characteristic of different classes, where healthy, this green line is showing the healthy trees, showing the lower reflectance value, with the higher in the reddish band here, and a disease band, disease trees are showing the higher reflectance value, with the early disease being the highest. On the other hand, grass here are showing totally different values, showing a very low reflectance value in all the bands. To make sure that whatever we are doing is correct and reliable, we also performed 2 susceptibility metrics. These metrics are Jeffreys Metosita distance and transform divergence distance, to check that our data is accurate and we are accurately classifying the data. We performed these susceptibility analysis, and result shows the higher value of JM metrics, which is more than 2. That means our data was accurately classified. And here we can also identify the importance of reddish and NIR band, which was also similar in the previous spectral profile. This slide is showing the classification result. Here table 1 is showing the accuracy assessment of artificial neural network and SVM classification. The support vector machine is showing outperform the overall accuracy and kappa coefficient as compared to artificial neural network for the study area. The overall accuracy for SVM is 92.48%, and kappa coefficient, which is an agreement between actual and predicted value, is 89.14. So here figure 5 is showing SVM classified map. Here you can clearly observe the green, that means healthy, pink, the early disease, moderate disease, and the severe disease for the study area. And these are the symptoms we observed in the ground. And in this study, we also found NDVI and SAVI vegetation indices, or the optimum spectral indices, for classifying these disease symptoms. So this is the result of our objective 2, individual tree detection in the study area. Here you can see figure number 7, BSNP severity distribution map with the individual tree detection. This is the result of one plot showing the total number of trees are 453 and are categorized into healthy, early, moderate, and severely diseased. And table 2 is showing the multispectral performance metrics for individual tree detection, where we got precision of 0.57, recall of 0.93, F-score of 0.71, and height mean error of 0.89 with the RMSE of 1.71. So to conclude this, this study demonstrates that when we combine the ground data with the multispectral imagery, it's a win-win situation to identify and map and even create a distribution map for such diseases. The major challenge was to the pre-confirmation of the pathogen from the laboratory analysis. And second was the analysis of very heavy data. And In future, we are going to work on the integration of lidar and satellite remote sensing. I want to acknowledge US Forest Service for providing us the financial support. I also want to acknowledge the guidance from my supervisor, Dr. Lana Narayan, my project mate, teammates, and all NASA HU team members for having us here today. Thank you so much.